fx be defined in x such that x belongs to R, x less than equal to 1 greater than equal to 0. That means this function is defined when x lies from 0 to 1. That means when the input, this one is from 0 to 1, then only the function will be defined, else not. Now, the first question is given. Find the domain of f of 2x minus 1. Now, what is the meaning? That this will be defined when 2x minus 1 less than equal to 1 greater than equal to 0. Now from that we can say 2x less than equal to 2 greater than equal to 1. And from that we can say x less than equal to 1 greater than equal to half. So domain of this given function is half to 1. These are required domain for this function because this can be defined when this input is from 0 to 1. So here this will be from 0 to 1. And then corresponding value of x you can find out. Now for the next part, it is given find the domain of f of x squared. Now here also this will be defined when this x square is less than equal to 1 greater than equal to 0. So we can say will be defined when x square less than equal to 1 greater than equal to 0. And then we can start directly. No need to write this. We can say x square less than equal to 1. Now, if square of a number is always greater than equal to 0, so there is nothing to do here. After that, you can say that x square less than equal to 1, or you can say x square minus 1 less than equal to 0, and then x plus 1 into x minus 1 less than equal to 0. Now, we can take a number line here. And we get this is minus infinity, this is plus infinity, minus 1 plus 1. Now we have plus power sign changes, power sign changes. So here x belongs to what? X belongs to minus 1 comma 1, and that is the required domain of this function. It is given the function fx equals to root over of x minus 2 and phi x equal to x plus 3. First of all, we are finding part 1, 1 by fx, which will be 1 by root over of x minus 2. Now, this is the function which you have got because fx is defined. So I can write 1 by fx will be also be defined when we have 1 by root over of x minus 2 as a rule of correspondence, and x minus 2 is greater than 0, x greater than 2. That is, x belongs to 2 to infinity. So part 1, 1 by fx, that is 1 by root over x minus 2. This is obviously true when we find 1 by fx, but here what is the domain? Domain is this. Here what is the domain? Domain is this. Domain is this means domain is obtained when x minus 2 is greater than 0. Here it is not equal to 0. Because when x minus 2 is equal to 0, this will be undefined. So x is greater than 2, that is x belongs to 2 to infinity. Next, part 2. It is given 1 by phi x. So it is 1 by x plus 3.
It's 1 by 5x, 1 by x plus 3. Now this will be defined when this is not 0. Because this is a linear polynomial, this can take any real value except the value for which this will be 0. So this is possible except when x is minus 3. So what is domain here? R minus set containing minus 2. Next, we come to the third part. It is f plus phi x, which is fx plus phi x, provided we take the domain of f plus phi function as domain of f, intersection domain of phi. Now here, what is fx? Fx is under root of x minus 2 and phi x is x plus 3. Now, if we find here separately the domain of fx, this is root over of x minus 2 will be defined with the largest possible domain, with the largest possible domain when x minus 2 greater than or equal to 0. This implies x is greater than or equal to 2. That is, x belongs to 2 to infinity. Now phi x equal to x plus 3 is a linear polynomial. So domain of phi x is R. So we get here domain of fx 2 to infinity, domain of phi x R. So when we take the intersection, we get here 2 to infinity, which is the required domain of a plus phi. So we can say, therefore, domain of a plus phi equal to 2 to infinity. Next, f into phi. Now f into phi x is fx into phi x, provided the domain of f into phi is equal to domain of f intersection domain of phi. Now domain of f we have already got, domain of phi also we have got, and their intersection part also we have got, which is 2 to infinity. Now here just we need to define the function, which will be root over of x minus 2 into x plus 3. It can be represented as like this also. Next, fifth one, f by phi x, which is fx by phi x, provided the domain of f by phi equal to domain of f, intersection domain of phi, minus set of those values of x for which phi x is 0. Now here we just substitute the value. fx is root over of x minus 2 by x plus 3. So here, what is the domain? The induction part we have already seen is 2 to infinity minus those values of x such that x plus 3 equal to 0. So it is 2 to infinity minus set containing minus 3. That will be ultimately 2 to infinity only. That is a domain of a by phi. So this is the definition of f by phi x, and this one will get the domain of f by phi. So this will be defined when this is the domain considered.
fx equals to 1 by log base 2 minus x plus root over of x plus 2. So here what you can do, you can consider here that it is the sum of the two functions. One is gx, one is hx. So here you can think this one as gx plus hx, where gx is 1 by log base e2 minus x and hx is root over of x plus 3. So you can say it is gx plus hx, where gx is this one, hx is this one. Now, for the domain of A, we have to find the domain of G and domain of H, and then you have to take the intersection. Now, Gx will be defined with the largest possible domain when 2 minus is greater than 0 and and log base e2 minus x not equal to 0. Now, this gives us what? X less than and 2 minus x not equal to 1. This implies x not equal to 1. Therefore, domain of G minus infinity, 1 union 1 to 2. Next, we move on to hx. hx will be defined with the largest possible domain when x plus 3 greater than equal to 0. So x greater than equal to minus 3. So x belongs to minus 3 comma infinity. This is domain of hx. Now, to get the domain of fx, we will take the induction part. So it is better if you take a number line and understand. Here the critical points 1, 2, minus 3. So x is saying that we will take the value from minus 2 to infinity. Minus 3 to infinity. Now from minus infinity to 1, open, and then from 1 to 2. Here, this is what we have taken but this is excluding 1. That is, 1 has not been taken into consideration, and this is up to 2, and here 2 is not taken into consideration. So if you see the common region here, that is DAG intersection DH, what we get? We get minus 3 comma 1 union 1 comma 2. That is the required domain of F. Fx equals to 1 by under root of x plus box 6. Now we will understand the meaning of this x plus boxes. We know what does the box gives us. The greatest integer which will come across while plotting the number on number line from left to right. That is, if we have a number line is the origin. Any number, suppose I take an example 1, and here we have 0.9. So when you take box of 0.9, this gives us what? This gives us 0. Why? Because from left to right, when we are coming to this point, the greatest integer we have come across. That is 0. Now, if we plot this, then how does it look like? All of you know. Minus 2, 1, 2, minus 1, minus 1. So graphically, what we observe, that is the graph. This is a graph of boxes. Y equal to boxes. Now, when x is greater than 0, not equal to 0, we are talking about greater than 0, then this is a positive quantity. And this would be non-negative quantity. When x is greater than 0, this is a positive quantity and this is a non-negative quantity. So whenever we take x greater than 0, you can see that both of them will be what? If we take the sum, because it is positive, this is non-negative. So sum will be what? Sum will be positive. So we see here that when x greater than 0, then or this implies x plus box 6 greater than 0. This implies 1 by under root of x plus box 6 is defined. Therefore, domain of f equal to open bracket 0 comma infinity. Gx equals to 1 by root under of x minus mod x. Gx equal to 1 by root over x minus mod x. For this, we will define this part first. So if we define x minus mod x, what does it mean? X minus under root of x square. And if we define this x minus x when x greater than 0, 0 when x is equal to 0, x minus of minus 6 when x less than 0. This gives us 0 when x is greater than equal to 2x when x less than 0. So this number is what? We are getting that this whole thing is giving us a value 0 when x is greater than or equal to 0. This will give us 2x when x less than 0. So this number is negative. This number is negative. So what does this show? That when it is positive number, we cannot take. When it is 0, we cannot take. When negative, then also we cannot take here. Why? Because when negative, then it is 2x, but 2x is negative because x is negative. So root over of 1 by root over of 1 by root over. So 0 cannot be put into this because then it will be the undefined thing. And if we take some negative number inside, then also it's not possible. If we represent this graphically, how does it look like? That is, if we represent x minus mod x graphically, it shows that this is y, this is x, this is origin, this is x prime, this is y prime. Now, when greater than equal to 0, it is 0. But when less than 0, then we have y equal to 2x. This is y equal to 0. And this one y equal to 2x. That means if we observe this x minus mod x always belongs to what? Minus infinity comma 0. So obviously when we are taking 1 by root over, then it will not define whatever x we put because root over of 1 by this is something, see if it is something 0 it is undefined. If it is negative number it is undefined. So what we conclude, for all x belongs to R, 1 by root over of x minus mod x is not defined. Therefore, domain of G is fine. Why? Because when it is positive on positive number, when the input is positive, then it is 0. When 0, then the denominator is 0. When less than 0, then it is 2x, but 2x is negative. So for any input, this gx is not defined. Hx equals to under root of x plus box x. Now it is root over of x plus box. That means here the input can be 0 also. Why? Because if it is x is 0, then the whole thing will be 0. In this case, what is that when x greater than or equal to 0, x plus box x is greater than equal to 0. And this implies root over of x plus box x is greater than equal to 0. That is hx is defined. Hx is defined. Therefore, domain of hx will be 0 to infinity. Even if we draw the graph and understand, then also it will be the same thing. If we draw the graph of here, y equal to box 6, then you can easily understand that when we take some value more than 0 or 0, the values are getting as 0 output or 1 or 2 or 3, that is like this, the integer value. So it is given, there is box x part. And when x is greater than equal to 0, that means this is greater than equal to 0 plus this quantity, which can be 0 also, which can be 1 also, which can be 2 also, or various values which you take more than 0. So ultimately, this is what non-negative quantity, this is non-negative quantity. So the sum will be non-negative. And under root of any non-negative number is defined. Hence the domain is 0, infinity. Phi x equal to root over of x minus box x. Now, x minus box, we have to analyze this one first. Just we take few values first. For example, for all x belongs to close 0, open 1, box 6 is what? Box 6 is 0. So this whole thing, phi x will become what? it will become x root over of x. Why? Because this whole part, this part is 0, so x minus 0, that will be x. Now, if we take y equal to x minus box 6, then in this case, y is what? Y is x. In this case, y is what? In this case, y is x in this interval. Similarly, if we take another interval for all x belongs to 1 to 2, open. Box 6 is what? Box is 1. So what is y? Y is x minus 1. Similarly, if we take another interval, minus 1 comma 0, box 6 is equal to minus 1. So y equal to x plus 1. So just in three interval, we have got y equal to x, y equal to x minus 1, y equal to x plus 1. Now in this interval, if we focus 0 to 1, so x greater than equal to 0, less than 1. But we say the x, that is ultimately the output cannot take the value 1. It is less than 1. Here, our x cannot take the value 2. So x minus 2 minus 1, y cannot take the value 1. But it can be greater than 0, greater than equal to 0. Because when you put x equal to 1, it will be 0. Next, this one. If you put x equal to minus 1, then y is 0. But we are not putting 0 exactly. It is less than 0, so y is less than 1. So what we understand, y equal to x minus boxes, this part is lying between 0 to 1. So if we represent this in graphical, graphical representation of only x minus box x prime. This is y, this is y prime, this is x, this is x prime. This is y equal to 1, because we have seen that output lies between 0 to 1, not touching 1. So if it is 1, this is 2, this is minus 1. If you draw the corresponding graphs, what is it? In this part, we have seen this y equal to x line. Already we have defined. Next one, y equal to x minus 1. And this one, y equal to x plus 1. Now, how to draw this? When y equal to x, you know, y equal to x minus 1, you can take the points and plot if you want. And the shortcut is what? That is, if it is x minus something, if you have y equal to fx, and from that, when you draw y equal to f of x minus alpha, we shift the curve alpha unit towards right. Similarly, when we have y equal to f of x plus alpha, we shift alpha unit towards left. So here when x minus 1, that is alpha unit towards right, when x plus 1, alpha unit towards left. Similarly, for the other values also, the same thing will be obtained. If we complete this graph, then we can draw similarly. So this is y equal to x minus 2, y equal to x minus 3, y equal to x plus 2, y equal to x plus 3. So basically, the same type of graph will be getting, and for various portions. For example, in this case, when x lies from 2 to 3, box will be what? 2. Going from 3 to 4, box will be what? 3. So just we have put the value and we have got this graph. So from this graph, what we understand that whatever the value of x we take, that is whatever real number we take, then what we observe that values of x minus box x is always lying from 0, comma 1. It is not touching 1, but touching 0. That is close 0, open 1. Now, in this interval, definitely this is defined. That is when the input is this one, 0 to 1, this will be definitely defined. That is what we can say that root over of x minus box x is defined for all x belongs to R. Therefore, domain of phi x is R. Fx equals to 2 minus mod of x minus 2. Now here, for all x belongs to R, mod of x minus 2 is defined. Mod of x minus 2 is defined. This modulus function domain is R. And when x is belonging to R, x minus 2 also belongs to R. So it is defined. And with that, we can mention this also, that mod of x minus 2 is greater than equal to 0. So when this is having the domain R, 2 minus this one will also have domain R. Now we have to find range. Now as we know, mod of x minus 2 is greater than equal to 0 for all x belongs to R. So it's mentioned once. Minus mod of x minus 2. If we multiply by the minus sign, this will be less than equal to 0. Now if we add 2 on both sides, this is becoming less than equal to 2. Now this implies that f of x less than equal to 2. This shows that range is minus infinity comma 2 equals to. Now here is given gx equals to 1 by under root of x plus boxes. Now first of all, we find the domain here. X plus box x is greater than 0 when x greater than 0. Why? When x greater than 0, box can give the output 0 also. But when it's a positive number, with that if we add a non-negative number, it will be always greater than 0. This is positive when x is positive. This is non-negative when x is greater than 0. So their sum is positive. So after that, if you take the under root x plus box x, this will be also greater than 0. So we can write that we have root under of x plus box x greater than 0 less than infinity for x greater than 0 for all x greater than 0. Now if you take 1 by under root of x plus box x, it is less than infinity greater than 0. Therefore range is 0 comma infinity. Now for this part, that x plus box is greater than 0, you can take the help of graph also again. That's a boxes graph. You can represent it in this way, that is x prime y prime, and here it will take some value. Now when it is greater than 0, if x is in this case greater than 0, you can start it like this way, 1 and so on. Now here we have taken this semicircle because why? Because we are plotting the graph of y equal to box 6 here when x is greater than 0. So you can understand when x is greater than 0, output can be 0, it can be 1, and for further it will be 2, 3, 4, like that. That is, this is what this is a this part is what this part is a non-negative quantity. It can be 0 or any positive number. And x is what? X is a positive number. So the sum will be what? Always positive. Now this part, when this is greater than 0 less than infinity, for that you can take the help of 1 by x prime to understand that this is y, this is x prime, this is origin, this is x, this is y. Now here if we draw, this is the graph of y equal to 1 by x. Now, when x is the input, you can think this is the input. When the input is greater than 0, that means as it is very close to 0, then what you can see that as x is tending towards 0, the corresponding values of y is huge values going towards positive input. So when it's greater than 0, you can see the output is less than infinity. But that is why it's into a huge value, and input is what more than the value which you can imagine. So that is the reason what we are writing, that this is less than infinity, it's going towards a huge value. And when x is going towards infinity, the graph is tending to touch x-axis. It will never touch, because x will never, this input will never reach to infinity, and y will never touch x-axis. So when this is greater than, this is less than infinity, the output is greater than 0. Hence the range is written in. Is given hx equals to mod x minus 3 by x minus 3. Mod x minus 3 by x minus 3. So first of all, we consider here x not equal to 3 for sure, because when x is 3, this is undefined. In this case, the modulus function domain is R. This is a linear function, domain is R, but this cannot be 0. So we are taking any real value of x except 3. So here, x belongs to R minus set containing 3. Now here we can take two parts. If you take a number line and this is 3, then we have two regions. One is this region, one is this region. So case 1, when x less than 3, mod of x minus 3 equal to minus of x minus 3. Hx equal to minus of x minus 3 by x minus 3, which is minus 1. And when x is greater than 3, mod of x minus 3 equal to x minus 3. So from that, what we get, hx equal to x minus 3 by x minus 3. This is 1. Now, we have taken the whole real line into consideration. Because at 3 not possible, so we left out. And when greater than 3, that time we get the output as 1. When less than 3, output is minus 1. So the basically here we have two output, minus 1 and 1. That is the range of hx. So what we can say here, that range of hx is having 2 point, set point 2 point, minus 1 and 1. So if we represent this graphically, then this is x, this is y, this is x prime, and this is y. At 3, not possible, because that is not in the domain. So we consider greater than 3 and less than 3. So we have here y equal to 1 by, this is y equal to 1, this is 0 comma 1, and the other part y equal to minus 1, y equal to minus 1, is 0 comma minus 1. So from this what we understand that for in the range we have only two elements, minus 1 and 1. So this is the graph of hx equals to mod x minus 3 by x minus 3, x not equal to 3. So from that we get the ranges set continue minus 1 comma